Assalamu alaikum. So in this lecture what we will be doing is we'll be talking about two other proteins, and these are myoglobin and hemoglobin as examples of globular proteins. So before we proceed into the structures of these two proteins, let me tell you what the functions of the proteins are. The main function of myoglobin is to store oxygen in muscles. So basically, in cases of hypoxia, that is when oxygen pressure is very, very low in muscles, then myoglobin releases oxygen. Now, the oxygen-bound protein is known as oxymyoglobin, and the oxygen-free protein is known as deoxymyoglobin. Hemoglobin, on the other hand, functions mainly in transporting gases, mainly, of course, oxygen from lung to peripheral tissues, and on the way back it carries CO2 to lungs and then it gets exhaled. Now, hemoglobin also functions in blood buffering. Being a very dominant protein in blood, it can maintain a blood pH by absorbing or binding to and releasing protons. Now, these two proteins, myoglobin and hemoglobin, are holoproteins. I'm sure that Dr. Diala defined what holoproteins are, but basically let me define it again. So a holoprotein is a protein that has a non-protein group bound to it. Okay? Now, if this non-protein group is removed, then the protein is known as an apoprotein. Example includes lipoproteins. Now, in the lipid lectures, I'm sure you also covered lipoproteins. So, lipoproteins are proteins that are associated with lipids, and they are carriers of lipids in our system. If we remove the lipid part, then the proteins are known as apolipoproteins. Okay? So, myoglobin and hemoglobin are holoproteins. Specifically, they belong to a large group of proteins known as hemoproteins because they have a heme group associated with them. Now, this heme group is an organic molecule, and we'll talk about it in the next slide. Now, these hemoproteins belong to a large number of proteins again. You have electron carriers in the electron transport chain. We'll talk about these in next semester in the metabolism lecture. We also have sensor proteins, heme sensors, for example, gas sensors, and so on. And you have enzymes like the cytochrome P450 enzymes. Now, the heme group is also known as a prosthetic group. And a prosthetic group basically is a group, a non-protein group, that is bound tightly, or in other words, covalently to a protein. Now, this prosthetic group can be organic, like vitamins, sugars, lipids, heme as an example, or they can be inorganic, such as metals. Okay? But they're not composed of amino acids, and they are tightly bound, again, covalently bound. Now, this is the heme molecule. Basically, that's the heme molecule right here. It's basically the precursor of heme is a molecule known as protoporphyrin 9, except that it is associated with iron. And this iron is in the ferrous state. Now, the heme molecule is composed of 4 pyrrole rings. This is a pyrrole ring. So rings have names, like, for example, the imidazole ring in histidine, the benzene ring, for example. Another example is the indole ring of tryptophan. So you have 4 rings, and they're known as A, B, C, D. They're designated as A, B, C, and D. Right in the center, you have iron, and iron is bound covalently to the 4 rings having 4 covalent bonds. Now, also associated with, or what characterizes heme, is the presence of side chains. These are the methyl group, a vinyl group, and you have the propionate group. Note that the propionate group is negatively charged, but overall the heme molecule is hydrophobic and it is planar, that is, it is flat. Now, something else about iron is that it can form 6 covalent bonds. 4 of them are with the pyrrole rings, so you have 2 left. So let's move on and talk about myoglobin. So myoglobin is a monomeric protein, meaning that it is composed of just one single polypeptide chain. Now, in the center you have heme bound to it, and what characterizes myoglobin is that it is composed of 8 alpha helices, and these are designated from A to H. So you have A, starting with the N-terminus right here, you have the A alpha helix, then you have the B alpha helix, then you have the C, D, and so on, all the way to H. Between the alpha helices you have turns, so you have another secondary structure, but mainly it is composed of helical regions or domains. Now, just like any other globular protein, you have on the surface of the protein the mainly polar and charged amino acids. Right in the center of the molecule you have the hydrophobic amino acids. But there are 2 exceptions. That is, and these are known, and these are histidine residues. There are 2 histidine residues. And these histidine residues, they are hydrophilic, but they exist in the center, in the core of the molecule. And these 2 histidine residues are known as the proximal histidine and the distal histidine. So you have the proximal histidine in the F alpha helix, and you have the distal histidine in the E alpha helix. Now, whenever you notice that there are hydrophilic amino acids in the center of the molecule, it gives you an indication that these amino acids have a purpose. And the purpose of the proximal histidine, since it's the closer one to the heme, is it binds to iron. So this is the 5th coordinate. This is the 5th covalent bond that iron can form. Remember, you have 4 with the heme, and here you have the 5th one. Okay? Now, so again, this is another view. So you have the proximal histidine in the F helix forming a covalent bond with the iron, and you have the distal histidine in the E helix, and it's very close. It lies on the other side of the proximal histidine. Okay, and it overlooks iron. And the 6th coordinate that iron can form, the 6th covalent bond that iron form, is with the oxygen molecule. So notice the close distance between the distal histidine with the oxygen that is bound to heme. Now, something about the position of the heme molecule is that, remember I said that you have the propionate groups. These are the negatively charged groups. Now these 2 groups are they extend to the outside. They interact with the hydrophilic polar charged amino acids on the surface of the molecule, but the rest of the molecule lies inside the protein in what we know as the hydrophobic pocket. Now, something about the distal histidine is that it lies, as I said, on the other side of the heme molecule, on the other side of the proximal histidine, and it overlooks the position where oxygen binds to. Now the thing is that what the distal histidine does is that it can form hydrogen bonding with the oxygen. So what it does is that it stabilizes the interaction between oxygen with the heme molecule. Okay, so remember that this is purpose number 1 of the distal histidine. So as I said, you have iron in the ferrous state. It can form 4 covalent bonds, 4 with the pyrrole rings, and you have 1 with the proximal histidine, and the 6th one with the oxygen itself. Now, something important about iron is that it has to be in the ferrous state in order to bind oxygen. If it becomes in the ferric state, if it gets oxidized, then iron cannot bind to oxygen anymore. Something else is that the heme molecule gives blood the distinct red color that we know. Okay, so these lectures are concerned with knowing the relationship between structure and function. In other words, the purpose of amino acids. Now, what's important about is that the heme molecule is a hydrophobic molecule, so it fits in the hydrophobic pocket. Okay, so the hydrophobic amino acids that surround the heme molecule stabilize the interaction between heme with the protein. Something else is that the heme molecule itself supports the structure of the myoglobin protein by forming these covalent bonds with the covalent bond with the proximal histidine and stabilizing the hydrophobic amino acids that surround it. So it is a win-win situation. Remember how I said that the distal histidine stabilizes oxygen interaction with oxygen interaction with iron. Something else is that distal histidine functions as a gatekeeper. So it allows for oxygen to get in, and it prevents other molecules from getting in as well. So there is preference for oxygen entry into the hydrophobic pocket. Something else that is important about the hydrophobic amino acids that surround the heme molecule is that they prevent the oxidation of iron when oxygen is released. So usually what happens when oxygen is released, the molecule, like iron, becomes oxidized. But because this iron is surrounded by hydrophobic amino acids, it does not get oxidized. And remember, I said that in order for iron to bind oxygen, it has to be in the ferrous state. It should not be oxidized. Now, there's something else about distal histidine, and that is binding to carbon monoxide. If you have a free heme molecule and you add carbon monoxide and oxygen to that heme molecule, carbon monoxide has much higher affinity towards heme. So it has many orders of magnitude. That is, we're talking about a logarithmic scale. We're talking about like 1,000 or 10,000 times higher affinity for carbon monoxide than oxygen. Now what happens is that, and usually carbon monoxide, by the way, binds to molecules, and it likes to be kept in a straight position. But what happens is that because heme is part of the myoglobin molecule, and because it overlooks the histidine, the distal histidine, there is repulsion that is created between carbon monoxide and the distal histidine. So carbon monoxide binds at an angle which is not preferred at all by carbon monoxide. So that weakens the affinity of carbon monoxide to the heme molecule. So instead of thousands of thousands of orders of magnitude relative to oxygen, carbon monoxide has only 250 times more affinity or higher affinity than oxygen. So why is it that we don't die? Because the level of carbon monoxide in our body is very low. So oxygen wins the competition. In fact, in our body, carbon monoxide occupies only 1% of hemoglobin. Okay? But if distal histidine does not exist, then it would occupy 99% of hemoglobin. It wins the competition. Now, something about oxygen is that it prefers its interaction with iron to be at an angle. So there is a high affinity, good affinity of oxygen towards binding to heme. Remember this hydrogen bonding between the distal histidine and oxygen as well. Now, let's connect biochemistry to real life. Now, the thing is, we hear a lot in Jordan about cases of death as a result of heaters. Now, what happens with these heaters is that they produce a lot of carbon monoxide. So, when people stay or sleep overnight with heaters on, they get poisoned as a result of the carbon monoxide that is produced by these heaters. Now, it's also a case in the United States, for example, where people keep their cars in garages, especially in the winter. So they wake up in the morning and they turn on their cars to get them warm, okay, so that they would get to work. Now, cars produced carbon monoxide, and the garages usually are closed. So when they, after turning on their cars for some time, like 10-15 minutes, and they get into the garage, there are cases where they get poisoned as a result of this carbon monoxide that is produced by these cars, and it exists at very high levels in these closed garages. I'm not giving you ideas, but it's very common that people who want to commit suicide, they connect a hose from the exhaust to inside the car, and they close it. They close the car, and they sit in their car waiting to die. Again, I'm not giving you ideas, and don't do this before the biochemistry exam. Okay, so I said that the purpose of the function of myoglobin is to bind to oxygen and to release it in cases of emergency, that is hypoxia. So you would expect, so if I tell you, how would you expect oxygen binding to myoglobin to be? Would you expect it to be at high affinity or low affinity? Now, your answer should be, it should be at high affinity. so that it does not get released unless the pressure of oxygen, the amount of oxygen in tissues, is very, very low. And that is exactly the case. So this is known as the oxygen saturation curve. So in the x-axis, you have the amount of oxygen in torrs, or millimeter of mercury. Now remember, it's gas, so it's measured as pressure, not concentration. And in the y-axis, you have the fraction of saturation. That is the fraction of myoglobin molecules that is bound to oxygen. So 0%, 50%, and 100%. Now, look at the oxygen saturation curve. It looks hyperbolic. So the shape of the plot is known as hyperbolic. Okay? Now, what it means, and if you look at it, notice that almost 100% of myoglobin is saturated when you have only 25 torrs of oxygen in tissues. Okay? Now, there is something in biochemistry as well as pharmacology and toxicology, and that is the 50% mark. The 50% mark gives you an idea about things like affinity of binding. What we mean by affinity is strength of interaction, how strong two molecules interact or bind to each other. Now the 50% mark gives you an idea about the affinity. So the idea is, what is the P50? That is, what is the pressure of oxygen where 50% of myoglobin is saturated or bound to oxygen. And so you look at the 50% mark, you go here, you go down, and you look at the x-axis and you say it's 2 torr. So the idea here is that if I ask you, what is the P50? What is the what is the pressure of oxygen where 50% of myoglobin is bound to oxygen? You say it is 2 torr. The pressure of oxygen that is needed to fill 50% or to saturate 50% of myoglobin molecules is 2 torr. And this is very low, meaning that the affinity is high. In other words, you need very little oxygen to saturate 50% of the myoglobin molecule. So you need very little, meaning that the affinity is high. I hope that this is clear. Now, so let's talk about hemoglobin right now. Hemoglobin is different than myoglobin in function. That is, the main function of hemoglobin is to transport oxygen from lungs to peripheral tissues. Remember that. So myoglobin is a monomeric protein, but hemoglobin is a tetrameric protein because it is composed of 4 polypeptide chains bound to each other. Okay? Now, the other thing is that the 4 chains belong to 2 types, and these are known as the alpha globin chain and the beta globin chain, or polypeptide. So you have 2 of each. So the hemoglobin molecule is known as an alpha 2 beta 2 protein because it has 2 alpha chains and 2 beta chains. Now these alpha and beta, by the way, these are designations. So for other proteins, they can also be composed of alpha and beta and gamma chains, but they are different than the alpha and beta of the hemoglobin molecule. So these are just designations. So you have two beta chains that you see in here in blue, and in orange you have the two alpha chains. Now each one of these chains contain a heme molecule. So you have 4 heme molecules per chain, per polypeptide chain. Now something else about the alpha and beta chains is that they are also composed of many alpha helices. The alpha chain is composed of 7 alpha helices, and the beta chain is composed of 8 alpha helices. And these helices are also designated as A, B, C, D, etc. So all the way to H for the beta chain, and G in case of the alpha chain. Now something else is that the alpha chain is composed of 141 amino acid residues, but the beta chain is composed of 146 residues. Remember this 146 number right here. Now, something else is that the beta chain, the beta globin chain, is similar in structure to the myoglobin molecule. So there is a good similarity in structure between the myoglobin molecule and the beta globin polypeptide chain. So how are these subunits connected to each other? How are these polypeptide chains connected to each other? Basically, a hemoglobin molecule is a dimer of dimers. So what you have is an alpha beta dimer interacting with another alpha beta dimer. Now the alpha and beta polypeptide chains within this dimer are linked to each other via hydrophobic interactions. So you have hydrophobic interactions between these two alpha and beta, and you have hydrophobic interactions between these two alpha and beta. But these two dimers interact with each other via hydrogen bonds and electrostatic interactions. Okay? So can you have hydrophobic or non-polar amino acids on the surface of molecules? And the answer is yes, you can have them, and usually they have a purpose, and the purpose in this case is to have these chains, polypeptide chains, interact with each other. Now, so let's relate structure to function. The idea is that the purpose of hemoglobin is to transport oxygen from lungs to tissues, and then it carries CO2 back from tissues to lungs. Now the thing is, the pressure of oxygen in lungs is about 100 millimeter of mercury or 100 torr. On the other hand, the amount of oxygen or oxygen pressure in tissues is about 40, and it can go down to 30 torr. Now the question is, should hemoglobin have very high affinity for oxygen or very low affinity for oxygen? Now the thing is, if it has high affinity for oxygen, then it would bind very efficiently in lungs. It would bind very efficiently to oxygen in lungs, but then when it goes to tissues, because it has high affinity, it cannot release this oxygen very efficiently. On the other hand, if hemoglobin has low affinity for oxygen, then it would not be saturated in lungs, so when it goes to tissues, there is hardly any oxygen to be released. So insufficient oxygen is released. Now, the answer is hemoglobin has both characteristics. It has high affinity and low affinity state for oxygen. How is that possible? Well, if we look at the oxygen saturation curve for hemoglobin, it looks what we call sigmoidal. Okay, so this is hyperbolic for myoglobin and sigmoidal for hemoglobin. So it looks like an S, the letter S. Now, what a sigmoidal plot means is that the protein has two states or two structures. At low oxygen pressure, it has a low affinity state. At high oxygen pressure, it has a high affinity state. And that makes sense. So now in lungs, where the oxygen pressure is high, hemoglobin binds very efficiently to oxygen because it has high affinity. But at low pressure, when hemoglobin reaches tissues, it has low affinity towards oxygen and oxygen is released. Very smart. Okay. And it turns out that the P50 of hemoglobin towards oxygen is about 26 torr, or millimeter of mercury. So it's around here. But the pressure in tissues is higher, by the way. It's about 30 to 40. So how is it possible that hemoglobin has two affinity states, a high affinity state and a low affinity state? And the answer is because hemoglobin has two structures. So these are the two structures. So hemoglobin switches between a structure that is known as a T state and a structure that is known as the R state. Okay. Now this little shift has huge impact on the function of hemoglobin. Now because hemoglobin has two structural states, we call hemoglobin an allosteric protein or an allosteric molecule. Now allo means different or other. Steric comes from stereo, which means shape or structure. So if I say that hemoglobin is an allosteric protein, it means that hemoglobin is a protein that has different structures. Now these two structures again are known as the T state and the R state. T stands for taut or tense or tight, meaning that the molecule is not and this is the state where hemoglobin has low affinity for oxygen. Now the other state is known as the R state, and R stands for relaxed. So the molecule in the R state has very high affinity, about 500 times higher affinity to oxygen than if it is in the T state. So when the molecule is relaxed, it can bind to oxygen with high affinity, but if it is tight or in the T state, then it has low affinity for oxygen. So what happens is that in lungs, hemoglobin presumes the R state, the R structure, the high affinity structure, and when it reaches tissues, it switches to the T state or the low affinity affinity state, and oxygen is released. So let's look here at the oxygen saturation curve. At low pressure, hemoglobin is in the T state. It has low affinity to oxygen. At high pressure, now hemoglobin is in the R state and it has high affinity to oxygen. Okay. Now, notice the change between the deoxy and the oxy is really very little. What you see is a shift by 15 degrees only. This shift is what makes hemoglobin having a high affinity towards oxygen. So what we're going to do now is zoom into the structure of hemoglobin to see how the switch takes place. And I hope that you will appreciate biochemistry at this point. See, what happens is that when hemoglobin is not bound to oxygen, the heme molecule has a dome-like structure. So it looks like a dome, قبة. Okay, it's not straight. You can see it here as well. So what happens now? This is the proximal histidine. Right below, you have the distal histidine. So what happens is oxygen comes in, it binds to iron, and what it does is that it pulls the heme, it makes it straight, and it pulls the histidine along with it. So this histidine, the proximal histidine, is pulled down. So again, you see oxygen bound to iron. Now heme looks flatter. It doesn't have this bent structure anymore. And you have this histidine pulled further away from the helix. Now, what happens then is that you have everything changing. You have this movement of the helix, and this movement of the helix results in changing the tertiary structure of this polypeptide, and that changes the whole structure of the molecule. So you have basically change in the structure of the heme molecule that changes the secondary structure, the alpha helix, that contains the proximal histidine, that changes the tertiary structure of the polypeptide that is bound to oxygen right now, and that changes the and that changes the quaternary structure of the whole molecule. So changing secondary, then tertiary, then quaternary structures of the hemoglobin molecule. Exactly what happens is that you have breakage of the electrostatic interactions between the chains. Remember how we said that the dimers, the two dimers, interact with each other via electrostatic interactions. So what happens is that you have breakage of these electrostatic interactions, and the molecule becomes relaxed. So you have less interactions among the different amino acids, and the molecule becomes relaxed in the R state, and it changes to the higher affinity state. Okay, so again, heme is bent, oxygen binds, heme becomes straight, it pulls the proximal histidine further away from the helix that it's bound to. That changes the structure of the secondary structure of this alpha helix, and that changes the structure of the whole molecule by breaking these electrostatic interactions. Another view, the electrostatic interactions are reduced in number and the molecule becomes relaxed. So you can take a moment to read the text in this figure. Now, let's zoom in further and look exactly what happens how these electrostatic interactions are broken. So what happens is in the T state, the C-terminal histidine 146 of the beta globin chain forms two ion pairs, two electrostatic interactions. Remember, we said that the beta globin chain contains 146 amino acids. The very last one is histidine, and it's known as histidine 146. Now, since histidine is the last one in this polypeptide chain, it has two opposite charges. It has a positive charge on the R group, and it has a negative charge on the carboxy terminus, right? So the negative charge on the carboxy terminus of that histidine forms an electrostatic interaction with lysine on the opposite chain, that is the alpha chain. So you have this electrostatic interaction between beta 2 and alpha 1, between the histidine 146 and a lysine. Now, the positive charge on the imidazole ring of histidine forms another electrostatic interaction, but with an aspartate that exists in the same chain of the beta globin chain, the polypeptide. Okay, another look. Here you have histidine, the very last histidine in the beta chain. This histidine can form an electrostatic interaction between the carboxyl group, that is the carboxy terminus of the histidine of the polypeptide, with lysine on the opposite chain, that is the alpha chain. And you have the imidazole ring right here forming electrostatic interaction with an aspartate within the same polypeptide. Great. So what happens is that when you have this, when oxygen binds and you have change in the structure of the heme molecule and you have movement of the helix, that results in sliding of the alpha and the beta chains away from each other. So these electrostatic interactions are gone, and you have so right here you have the histidine or the alpha chain now slides away, and you have loss of the electrostatic interaction between this histidine and this lysine. And you have also break in the interaction between the histidine and the aspartate within the same chain. Rather, you have formation of a hydrogen bond between an asparagine on the beta chain with an aspartate on the alpha 1 chain. So you have loss of electrostatic interactions and formation of a hydrogen bond. Now, these electrostatic interactions that are formed between histidine and the other two residues stabilize the T state of the hemoglobin molecule. And formation of the hydrogen bond between asparagine on the beta chain and aspartate on the alpha chain stabilizes the R structure of the hemoglobin molecule. Now, something else, and remember that whenever you see a sigmoidal curve, it means that binding is cooperative. Okay, it means that one, there is change in the structure of the molecule, that's one. Two, it means that there is cooperativity as well. What we mean by cooperativity is that binding of the first oxygen molecule to hemoglobin makes it easier for the second oxygen molecule to bind to the second site. And that makes it even easier for the third oxygen molecule to bind to the third binding site, to the third heme. And that makes it even easier for the fourth oxygen to bind to the hemoglobin molecule, to the heme, that is. Okay? So that exactly what we mean by cooperativity. Okay, so we said that hemoglobin is an allosteric protein, meaning that it has different shapes, the high affinity state or structure and the low affinity state or structure. Now, these allosteric proteins, and later on we will be talking about allosteric enzymes as well, these allosteric proteins are regulated by molecules small molecules known as allosteric regulators or effectors. Now, these allosteric effectors or regulators can either be homotropic or heterotropic. Homo means the same. Hetero means different. So if the regulator is the same as the ligand, ligand is a small molecule that binds to a protein or to a receptor, for example. Okay, so if the effector, if the regulator and the ligand are the same, then we say that this is a homotropic regulator. So what happens in case of hemoglobin is that oxygen plays the role of a regulator. It stimulates, it induces, it makes it easier for a second oxygen molecule to bind. So it is the same, the effector is the same as the ligand, and we say that this is a homotropic allosteric regulator. Now, next lecture, we'll be talking about other regulators like protons, bisphosphoglycerate, and so on. And these regulators, what they do is that they bind to hemoglobin and they do change the affinity of hemoglobin towards oxygen. So the regulators are different than the ligand. The protons, the bisphosphoglycerate, the CO2, and so on, they are different than the ligand, which is oxygen, and these are called as heterotropic allosteric regulators. Now, these regulators, by the way, can have a positive effect or a negative effect. In other words, if we say it has a positive effect, it means that when it binds to the molecule, it makes binding of the ligand easier, or it increases the affinity. That is, affinity means strength of binding or interaction. If it has the opposite effect, that is, if binding of an effector makes it harder for the ligand to bind to the protein, then we say that it is a negative allosteric effector or regulator. And you can see this in this image or picture right here. So I have a protein. It binds to a negative allosteric regulator. It makes it hard for the ligand to bind to the protein. Okay. Now you can also have a positive allosteric regulator that can bind to a protein, and it makes it easier for a ligand to bind. So this is a positive allosteric regulator. This is a negative allosteric regulator, and both of them are heterotropic allosteric regulators. Now, in case of homotropic allostery, you have binding of a ligand or an effector. It influences, it induces, stimulates, it makes it easier for a second ligand to bind. In case of hemoglobin, it makes it easier for binding of 2, makes it easier for a third one to bind. Binding of 3 makes it easier for the fourth one to bind. And that's cooperative regulation. Now, so all we talked about so far is a hemoglobin molecule that is made of two different chains. We have 2 alpha chains and 2 beta chains. But this is not really the whole story. Rather, there are different hemoglobin molecules that are produced throughout our life. And the production of hemoglobin starts early on in the embryonic stage. That is, even in the first week of development. Now, what happens is that you have production of two different chains known as epsilon and zeta, and they are produced from the yolk sac. And their production declines with time, and you have production of the alpha chain and production of another chain known as the gamma chain. And they are produced from the liver and later on from the spleen. Now the beta chain starts to be produced also early on, but it increases, its production increases right before birth. At birth, note that at birth, you have more gamma than beta. So alpha continues throughout life. Gamma, production of gamma declines with time. Production of beta increases as we grow older. And you also have production of another globin chain known as the delta globin chain. Okay? So, in the embryonic stage, hemoglobin synthesis begins in the first few weeks, and production occurs from the yolk sac. Now, the major hemoglobin is a tetramer composed of two zeta and two epsilon chains. And it's also known as HBE, E for embryonic, goer 1. Now, you have also other forms that exist because you have production of alpha, you have production of gamma, and you have production of beta, but these are minor forms. So you have HBE goer 2, alpha 2, epsilon 2. You have HBE Portland 1, zeta 2, gamma 2, and you have HBE Portland 2, zeta 2, beta 2, but these are minor forms. Now, but in the fetal stage, by 6 to 8 weeks of gestation, you have production of the gamma polypeptide. So the major form of hemoglobin is now known as HbF for fetal, and it is alpha 2 gamma 2. Remember that the alpha polypeptide continues to be synthesized throughout life. Now, right before birth, you have this switch into the beta globin. Still, HbF makes up most of the hemoglobin molecule at birth. Okay. Now, in adulthood, HbF makes up about 1% of all hemoglobin molecules. And production of gamma and beta chains occurs in the bone marrow. Adult hemoglobin, we have two forms, and these are known as HbA. A stands for adult. HbA1, which is made of two alpha chains and two beta chains. And you have another minor form known as HbA2, which is made of two alpha chains and two delta chains. But the majority is HbA1. What's interesting is that scientists have found out that HbA can be glycosylated. We're talking about HbA1 in particular. So HbA1 becomes glycosylated, and this glycosylation occurs at the N-terminus amino acid of the hemoglobin, of the beta chains. The first amino acid of the beta chain is a valine. So at the N-terminus, at the N group, you have attachment of a glucose molecule. Okay. Now this glycosylated hemoglobin is known as HbA1c. All right. Now, and scientists have found out also that people with diabetes who have high level of sugar in their blood also have high level of the glycosylated hemoglobin, that is HbA1c. And as a result, HbA1c is now a marker for diabetes. بالعربي it's known السكر التراكمي. So what's the advantage of testing for the glycosylated hemoglobin? Now, there are two ways by which we can check diabetic patients. We can look at fasting glucose level. That is, we let the person fast overnight. Next day, they come and they do the blood test, and it tells us the level of glucose at this particular moment. So if this person has breakfast, the test is ruined because the glucose level would be very high, and that's why they have to fast overnight. But by doing the glycosylated hemoglobin test, it gives us a better picture about the control of sugar that this person has. So it gives us an idea of what has been happening over the past 2 to 3 months. So let's say that a person comes in with diabetes, we give this person a medication, and we ask this person to do another test after 2 months. Now, after 2 months, by looking at the level of glycosylated hemoglobin, we would be able to tell if the medication is working or not. We would be able to tell if the person is abiding to instructions or not, if this person is following instructions or not. Now, the level of glycosylated hemoglobin can be expressed in different ways. Now, the old way is known as the DCCT, and using DCCT units, and usually they are percentages. Now, the new method of expressing level of glycosylated hemoglobin is known as the IFCC method. Okay, so although glycosylated hemoglobin test is good, it doesn't tell us about what has been happening over a short period of time right before the test. It doesn't tell us about exposure to hypoglycemia or hyperglycemia at certain moments during these 2 to 3 months. So one day, for example, of high sugar intake would not really affect much the level of the glycosylated hemoglobin. We're talking about a long period of hyperglycemia, that is high level of glycemia or sugar intake that this person is exposed to. Okay. Now this table is very important for you to know, and I do want you to memorize it. So it tells us about the status of individuals, whether they are normal, pre-diabetic, which basically it makes them susceptible, it makes them vulnerable, it makes them easier to become diabetic, or if a person is already diabetic, and there are different levels, of course, being mild diabetes or very severe diabetes. So these individuals can be put in these categories according to the amount of blood glucose, that is fasting glucose, or the amount of glycosylated hemoglobin. So normal individuals, if they fast overnight and they do a glucose test, they should have a level that is about 120, about 80 to 120 milligrams per deciliter of glucose, which is equal to about 5.4 to 7 millimole per liter. These are normal individuals. Now, in terms of glycosylated hemoglobin, normal individuals should have about 5 to 6% of hemoglobin being glycosylated, which is equal to 31 to 42 millimole per mole. This means the percentage of hemoglobin, a glycosylated hemoglobin per total hemoglobin, and here you have millimole of glycosylated hemoglobin per total moles of hemoglobin. Now, pre-diabetic people, individuals, have a level of glucose that is higher than normal, about 150, 155, which is equal to about 7% in terms of the DCCT measurement, or according to the IFCC criteria, about 53 millimole per mole. Now, for diabetic individuals, they have very high levels, about 180 and above. Of course, the higher the glucose level in blood, fasting glucose that is, and the higher HbA1c is, whether we're talking about percentages or concentrations, the more severe the disease is. Okay,